Ciao everyone, it's Vicky here, and in this tutorial I'm going to talk about classical mechanics for FX animation, so physics. So first of all, what is an FX animation? We use FX animation to create things such as fire, smoke, debris, fracture simulations, liquids, particles, so snow, sand, and so on and so forth. So FX animation is recreating the behavior and motion of real objects in a computer software. So we are using Houdini to recreate things that we can observe in real life, such as water or fire, and so on. And what does classical mechanics mean? So classical mechanics is the study of universe and the forces around us. So it observes our universe and then explains why objects move in the way they move, and also try to predict its behavior, so the behavior of objects such as liquids, so water. All right, so why can we see maths and physics in the VFX world? How is it relevant? Well, first of all, in the 3D world, so 3D VFX world, we use a Cartesian coordinate system, so X, Y, and Z axis, and then we move our objects in that space. So when we model or we create 3D things, they are always in this Cartesian coordinates system. We use that system to navigate, to move them, to scale them, to model them. And why is this relevant? Well, first of all, if you want to create something that happens in real life, so you can observe it in real life, you need to be able to describe it and break it down. So if we have a liquid simulation, you need to know how liquids behave, for example, when put in a jar or a bottle. And then you need to be able to translate this information to a 3D VFX software. So without that knowledge, it would be very difficult to create something realistic in 3D software. So physics and maths are very important tools to help you create 3D things and FX animation, for example, in Houdini. So some laws of physics have been described by the Greeks, but we know now that most of them were wrong. However, the first person to develop theories that actually worked and still work today, so people still use it today, is Sir Isaac Newton, a mathematician, astronomer, philosopher, alchemist. So he observed the world around us and then tried to describe it and write down what he sees. And in the 17th century, he presented something called the 3 laws of motion. The first law, called Newton's first law or law of inertia, states that every object persists in its state of rest or uniform motion in a straight line unless it is compelled to change that state by forces impressed on it. So if we translate that to English, it means that an object in motion will remain in motion and an object at rest will remain at rest unless acted upon by a force. So you can imagine that when you're ice skating, it's very difficult to stop because the ice is very slippery. So if we simplify it, you can even say that there are no forces acting on you. So you're just remaining in motion when you start. Okay, unless you hit the wall, then you stop because the wall acts on you with a force. Okay, so let's see how this works in Houdini. So in Houdini, the first thing I'm going to do is, of course, change the desktop type to technical and not tops, technical, sorry, and close these 2 panes just because my screen is too small. And now I want to start creating my network. So what I will do here is drop down geometry node and rename that to ball geo. Okay, and then I want to dive inside and drop down a sphere. Okay, so I will change the primitive type of the sphere to polygon mesh just because we're working with a simulation, so it will help us a bit. And then I want to create transform node after the sphere, make sure to display it, and I will slightly zoom out and move my sphere up, so in y-axis. You can see the axis here, so we have x, y, and z. So I want to move it up, so it's y-axis. The same in here, I have x, y, and z. So you can see we're using Cartesian coordinate system, and I will use 5 in y-axis, so it moved up. Okay, and the next thing I want to create is a null object, null node, and I will rename that to out ball. So I'm using null because Houdini, in a second, when we use the shelf tool, will add some more nodes in here. So null allows us to add, if we want to edit the sphere or add more things here, we can do it very easily by adding things here at the top to the null. Whereas if you don't have it, the shelf tool will connect all the tools straight to the sphere, for example, and it will be very difficult to adjust it later on. So it's always a very good idea to have the null node at the end of your network, and make sure to display it because the rest of the network will be connected to the displayed node. Okay, now let's go back to the object level, and I will select the geometry I want to add to our simulation, and let's have a look at the rigid bodies tab. So when you open the rigid bodies tab, you will see a lot of tools here, but the one we want to use is RBD objects. When I hover over, it gives me a description of what it does, and it says that it creates one or more rigid bodies from subgeometry. So subgeometry is our surface operator, so this one over here. Also, if I hover over and press F1, it will open Houdini Guide. And in the Houdini Guide, you can read a bit more about this node. You can also see other nodes. So it has a list of all nodes in Houdini, also some vex functions. So if you don't know what something does or you want to learn more about it, it's always a good idea to search there. So what RBD object does is it adds this geometry, so in our case the ball, to the simulation, and it allows all the forces in our scene affect this geometry. So for example, gravity, and it will fall, or maybe we have wind, so it will go to the side, and so on and so forth. Okay, so let's do it. Select the geometry, click on RBD object, just give it a while to load, and now you will see a new network which is called Autodop network, which is a dynamic network. All things to do with our simulation, most of the most important things are hidden here. Okay, so when I add more objects later on to our simulation, they will be added to this network as well. But first, let's see what happened, what changed in our geometry. So when I open it, you can see the null is here, and then I have these 3 nodes added by default by Houdini when I use the shelf tool. Alright, so now we can see why it's so important to use the null. And then in Autodop network, so let's dive in, I also have more nodes. So let's go from the top. So the first one is ball geometry. I renamed it, so in the object level, it's called ball geometry. So this is why this is also called ball geometry. So this ball geometry is this sphere over here. If I want to change the physical properties of the sphere, I can do it in here. We'll do that a bit later. Then I have merge node, just because I might want to have more geometries linked to my simulation, and they will be linked to the merge node. And then I have a very, very important node, which is called, in this case, rigid body solver. And in every type of simulation, you will have some sort of a solver. And the solver is a brain of our simulation, hence the little icon here. In this case, it's rigid body solver, so rigid body brain, but you can also have pyro solver for fire or pop solver for particles, and so on and so forth. So solver is what calculates our simulation. It solves our simulation. It's very, very important. Then we have another merge node, and then we have the gravity force or gravity field. So by default, you can see that it's set to -9.80 and so on, and this is the Earth gravity force, but you can change it. You can even get rid of the gravity force if you want to, okay? So we can adjust it. And again, we have the same X, Y, and Z. So at the beginning, by default, it's set to minus in Y-axis, so it's pointing downwards, so all the objects will fall. And then we have the output. Okay, great. So let's go back to the object level, and the first thing we want to do, actually, we should have done it at the very beginning before even starting the simulation, but we'll do this now. We need to make sure that our animation options are set correctly, otherwise the simulation will not work correctly. Okay, so we can go to either clicking this icon, or we can click Alt, Shift, and G. And this will open global animation options, and we need to make sure that the frame rate is correct, and also we need to make sure that we play every frame. So real-time playback, play every frame, but never faster than FPS, and you can save it as default. And the reason why we need that is because in simulations, Houdini needs to calculate every frame, and if we skip frames, the simulation is not going to be correct. All right, so now with these settings set up, we can play the simulation. And now you can see what happens. So the sphere falls. I will zoom out so they can see it. Okay. So it falls, and because we are using a gravity force, it will start slowly and then it will speed up as it goes. Okay. So gravity force gives this ball an acceleration, and we want to check what the first Newton's law says. So we need to do something else. We need to get rid of all the forces, because the law says that an object in motion will remain in motion and an object at rest will remain at rest unless acted upon by a force. So we don't need any forces here at the moment. So let's go to the Autodesk network, and I will hold this gravity node, shake it to the sides and disconnect it. Okay, so now it's not affecting our geometry. We can play and see. Okay, or I can link it back again and then use the bypass option. Okay, and this will also skip this gravity node. And what you can see here is that the timeline changed color to orange, and this is one of the tips for you when doing simulations, is that the timeline changes color. So first of all, when you have your simulation and play it, the timeline will change color to blue, which means Houdini simulated something and saved it as temporary files on your computer so that you can preview it in more or less real time. Okay, so it doesn't have to simulate every time it starts, it just reads the files. Okay, but when I change something, so for example, gravity, add gravity again, it changes color to orange, which means that I changed something in my simulation, in the options, and the simulation is not up to date anymore. So I need to go to the beginning, usually just use this. Okay, I don't want to use the slider, I just want to click on this and then play the simulation again, and now it's up to date. Okay, so let me bypass gravity and then slightly zoom out. And what I want to add now is velocity. So let's select our geometry in the dot network and look at the options. So when you scroll down, you will see initial state, and we can set position, rotation, velocity, and angular velocity. I want to add velocity, and I want the sphere to move downwards. So I will use minus, for example, 5, and enter to submit. Then zoom out and play it. Okay, so now you can see how different it is to gravity force. Gravity force made the ball speed up, whereas when I just use the force of -5, it's the same for every point. So it just moves in linear motion downwards. And it will move like this forever. Unless, as the first law says, it's acted upon by a force. So let's add a force. Okay, and how can we add a force to our scene? So I'll go back to the object level and go to the second tab called collisions and create a ground plane. So you just click on the ground plane and it will add it to your network. Okay, so it created a new group called ground plane, and also in Autodesk network it creates this mess. So I can click L and H, and you can see we have the ground plane. It's set up for us, and also in the viewport it's kind of tiny, but you can see these arrows here. They tell you that the ground plane is huge. It's on the whole scene. Okay, it's not just that small, it's everywhere. All right, so let's see what happens when I play the scene now. So play. Okay, so you can see that the ball falls in linear motion, then hits the ground, so there is some force acting on it, and then changes direction and it goes up. And it will go up like this forever again, unless we place another geometry there and act upon this geometry by another force. So this is the first Newton's law. Brilliant. So let's go back to the object level and save your scene. So Control S. Brilliant. So what is the second law of motion. So the second law of motion states that force is equal to the change in momentum per change in time. For a constant mass, force equals mass times acceleration. This might seem quite confusing, so let's break this down. So it means that force is equal to mass times acceleration, and we could write it down like so. So the force of our sphere, or the force it applies to other objects, is equal to mass of the sphere times acceleration. So in normal conditions, the main acceleration is the gravity force, whereas mass is how much the object weighs. Okay, so there is a funny moment in Addams Family that they're trying to figure it out, and let's see.
Pugsley, the baby weighs 10 pounds. The cannonball weighs 20 pounds. Which will hit the stone walkway first?
I'm still on fractions.
Which do you think?
The cannonball?
Very good. But which one will bounce?
The baby?
There's only one way to find out. Ready?
Okay, so the one way to find out is to open Houdini again and check how it applies to Houdini. Okay, so to see how much force the ball carries, we need to create another object in here. So let's again go to the tab menu, create geometry, and this time I'm going to create a fractured geo. Okay, let's dive inside this geometry, and here I want to create a torus. Okay. And if you look at the options, you can see that by default it's set to polygon, so we can just leave it like this. And then the next thing I want to do is drop down transform, not trace, transform. Where is it? Transform. Here you go. Okay. And in this transform node, I want to use a very simple function to make sure that the torus is on the ground, because at the moment you can see it's intersecting with the ground. So let me go to the options, and in the Y position I will use $y min, all block capitals, and enter. So $y min, and now you can see that it moved it to so that it's level with the ground. But now when I increase the size of this torus, it starts intersecting with the ground. And this is because the pivot point is in the center, it's in here, and we need to make sure it's at the bottom of this torus. Okay, so let me change that back to 1. And now I will go to the pivot transform options, so it's a little plus button over here, and change the Y value of pivot translate to almost the same, just without the minus. So $y min, enter. Okay. So now it's nicely on the ground, and when I make it bigger, it also stays on the ground. Brilliant. So let me maybe make it a bit bigger, like so. Okay, so the last node we want to add here is of course null. So I'm dropping down null, and I'll rename it to out fractured. Okay, make sure it's displayed. And then I go back to the object level. And now what I want to do, because if I go to Autodop network, you cannot see your torus in here because we didn't add it to our simulation. So when I play it, you'll see that the ball just goes through it. It doesn't react with the torus. So I want to make sure that the torus is added to our simulation, and I'll do this the same way as I added the ball. So select the torus, go to the rigid bodies, and click on RBD objects. Okay, so I just clicked on it. And it might take a while, so let's check in Autodop network if it added it. Yes, here we go. So now we have the fractured geo, so our torus, in our network. And now when I play it, okay, you can see that when the ball hits the torus, they both move. Great. So what I want to do now is break this geometry. So again, I will select my geometry to break, and I will use this tool called Make Breakable. So let's click. And now you can see this line asking you to select RBD objects to make breakable and then press enter to complete. So our RBD object is this one here in our DOP network, so I can select it, then hover over the viewport and press enter. And you will see a new node pop up, which is the fracture parameters node. Okay, so let's play the simulation again and let's see what happens. Okay, now it's a bit slower because it has much more to calculate. Brilliant. So now we can see that when the ball hits the torus, it just breaks. It doesn't look natural because we don't have gravity force. We only have the velocity force that acts on the ball. So it moves it down. Okay, but we can see that the ball fractures, breaks the torus quite well. All right, so now let's see what happens if I change the density or the mass of the sphere. So I select the sphere, then go to physical options, scroll down and increase the density. So I'll just add one more zero, press enter. And in the torus, I'll reduce density like so. Okay, so how does it change now? Let's see. All right, so now we can see that it's broken and we have much more pieces. So the impact the sphere has on the torus is much bigger. And this is exactly what Newton said. So the force of the sphere at the moment equals mass times acceleration, and we increase the mass, so the force increased as well. So to increase the force, we can either increase the mass or increase the acceleration. All right, thank you everyone. That's it for today. During the next lesson, I will explain and show you in Houdini how we can use the third law of motion. But for today, that's it. I hope you enjoyed it.